Does time really move in a single direction? Most people think they already understand what time is. They say, isn't it just the time and space that Einstein talked about in Relativity? But have you ever stopped to question if what you believe is actually true? The truth is, most of us have no real idea what time even means. We watch the clock, we count the hours, but those ticking numbers aren't time itself. They're only symbols. It's like holding a thermometer and thinking you understand warmth itself. But time is far more complex and profound than we can easily grasp. In the next half hour, we'll peel back the layers of this mystery to see if traveling to the future or returning to the past could ever be more than science fiction. And this isn't just about abstract theory. Time is something we live and breathe every single day. But how often do we stop and question what it really is? It defines our moments, shapes who we become, and quietly dictates the evolution of everything around us, from our own lives to the universe itself. It's like a river, quietly but firmly pushing us forward. But here's the problem. Is time really what we think it is? Is it just a tool to help us understand the present and the future? Or is it actually hiding the deepest secrets of the universe? On the surface, time seems to be simple. The clock is ticking, and the calendar is flipping over day and night. We get up, eat, and go to bed day by day. Flip through the calendar and plan for next Tuesday's party. Time seems to be a framework for life. But the more scientists study, the more things go wrong. Modern physics tells us that time is not something that exists on its own. It's not a clock that keeps ticking. It's actually a companion of space. How do you say that? Imagine that space is like a boundless, invisible piece of cloth. It's flat on all sides, holding everything. Stars, planets, galaxies, even light have to crawl on it. And this piece of cloth is not just space. It also contains time. So the scientists gave it a name. Time and space are actually one. They are not two different dimensions. They are connected to each other. Where do we usually think space is? Left, right, up, down, close, far. What exactly is time? Yesterday, tomorrow, morning, evening. They sound like different moments. But science says they're not. Think of space and time as a vast sheet of fabric, tightly woven together. If you pull on one thread, the entire fabric twists and bends. That's the nature of space-time. This revolutionary idea was first introduced in the early 20th century, and it completely transformed how scientists viewed the universe. Before that moment, space and time were seen as two completely separate things, independent and unchanging. Time, people believed, moved forward at a constant pace everywhere, and space was thought to be an enormous, unmoving stage, a fixed background where all events in the cosmos played out. But that stable picture didn't last for long, because one man challenged everything: Einstein. He stepped forward and shattered the old way of thinking. In his theory of relativity, he revealed that space and time aren't rigid or lifeless at all. They are flexible. They can stretch, shrink, twist, or even loop around themselves. And this movement, this distortion, depends on the matter and energy within the universe. In other words, the more massive an object is, the more it makes the space and time around it respond. More importantly, gravity is not the invisible gravitational force we have always thought of. In Einstein's eyes, gravity is not a force at all. It's the quality that bends the space and time. As a result, other things slide along that curve. Does it sound a little explosive? It doesn't matter. We can continue to use the analogy of the previous rubber film. Imagine that you put a layer of rubber film on the table. This is space and time. Now you put a bowling ball in the middle of the film. It will press the film out of a curve because it is too heavy. This represents a large mass object like a star or a planet that bends space and time. Then you put a small ball on the edge of the film. the small ball will slowly slide towards the big ball. It's not because someone is pulling it. It's not because it's sucked in. It's because it's rolling down the slope of the film. This is Einstein's explanation. Gravity is not a force. It's the bending space and time that guides the movement of objects. In other words, large quantities of things change the shape of space and time. Other objects move freely in this bending space and time. The reason why we feel gravity is that we just saw the result of their trajectory. And what's more interesting is that this effect is not unilateral. It's not just a large object pulling a small object. The small object will also be pushed by space and time sliding along the curve. This curve is not just a curve of space, because time is also rolled in. After all, space and time are tied together. If a star is bent by a film, it's not just space that can be bent. There is also time itself. According to Einstein, time is not the uniformly fluid, always constant beater in our imagination. It's like space. It will also be stretched, compressed, or even decelerated because of the difference in the surrounding environment. There is no uniform time standard in the whole universe. What's more ridiculous is that in Einstein's relativism, time is not past, but the label of the future. These words, to put it bluntly, are just tools for us humans to describe subjective feelings. Physics itself doesn't care about this at all. In Einstein's relativism, you can't find which is the past and which is the future. It only describes one thing: how time changes, how it is stretched, compressed, or even twisted with space. That's all. In Einstein's view, time is a dimension. There is no fundamental difference between 3 dimensions of space. You can say that something is 5 meters north, 3 meters south, and 10 meters east. Then, you have to add another one. When did it appear? So, in the 4-dimensional space, you have to use 4 coordinates to really describe an event in the universe. 3 dimensions of space plus a dimension of time decide where it is and when it is. But here's the problem. We can go anywhere in space. Left or right, up and down. But what about time? We can only move forward in one direction. We are pushed by a force to move from one moment to the next. But in Einstein's relativistic mathematical world, time does not move. All the time points are like points that cannot be drawn. They were all there at the beginning. This theory will not tell you what moment it is now, nor which moment is more special. It just calmly shows you the time and space structure of the universe, including all the past, present, and future, all at once. So a very unusual idea appeared. Maybe time is not flowing at all. Maybe it just exists quietly. Just like all the positions in space exist at the same time, every moment in time may have been fixed there. We just go through them one by one in a certain way. But from the perspective of the universe, they have all been woven into this web of time and space. Einstein himself said, in the past, now, and in the future, it's just a stubborn illusion. He didn't say time is fake, but that we thought time would flow and disappear. Maybe it's just an illusion made up by our brains, not the law of nature itself. But here comes the problem again. If that's the case, why can we only remember the past, but not the future? Why doesn't a broken cup jump up and fight back by itself? Why do we always feel like time is moving forward? If the formula of physics doesn't talk about any moment at all, it doesn't say the most important thing now, and it doesn't say that the past is over, then where does our sense of direction come from? This is the famous question about the very nature of time itself. In Einstein's equation, time is just an ordinary coordinate with no fundamental difference. But our daily personal experience tells us clearly that time has a direction. It goes from the past to the future, always straight ahead, never looking back. We were born, grow up, get old, and finally die. We light a match, it burns to ashes, and it can't grow back. In the real world, there is always a sense of unresisting one way. And in order to understand where this sense of direction comes from, scientists don't look for gravity, nor do they rely on relativity, but turn to thermodynamics, a subject that studies heat and energy flow, especially one of the core laws, the second law of thermodynamics. It's very straightforward. In a closed system, the degree of confusion of the system will only get higher and higher. In short, everything will become more and more messy from being neat, and more messy from being orderly. For example, when you drop an egg on the floor, the shell shatters and the yolk spills out. That's a clear increase in disorder. Chaos takes over, and if you just waited, hoping the shattered shell and spilled yolk would somehow pull themselves back together into a perfect egg, well, in theory, it's not completely impossible. But the odds are so small, they might as well be zero. It's almost impossible for such order to return on its own. It is precisely this kind of one-way evolution, from orderly to messy, that makes time have a sense of direction in our world. This is the source of the arrow of time. And injury is not just about eggs. It has everything to do with everything in the universe. From star formation to ice melting to the continuous expansion of the universe itself, every process, every system is falling into a more and more chaotic state. The increase in injury constitutes the before and after we feel. It provides an arrow for time. Even in the basic law of physics, there is no place for this arrow at all. You can understand it this way, just like we are reading a book. The 10th page and the 5th page in the book exist at the same time. They are all printed on the paper. They are all real. But we can only read them page by page, from front to back. Similarly, in this space-time book of the universe, all the moments may have already existed. But because of the existence of injury, we can only read it in one direction. Interestingly, if you play the video of the broken egg backwards, you will immediately feel something is wrong. It's not just because it looks abnormal, but because this inverted image violates the law of injury. Because of this, we can tell at a glance whether a video is positive or inverted. We can tell because we can subconsciously identify the arrow of time. But things have become more strange. The basic law of physics. In fact, there has never been a ban on breaking eggs. They just tell you that the probability of this inverted process is small to almost zero, but it is not entirely impossible. From the perspective of the equation, time can be used in the right way, or it can be used in reverse, and the mathematics can be fully understood. What does this mean? It means that the unidirectional nature of time is not written in the equation of the universe. It is more like the phenomenon we see, which is created by the arrangement of things and the operating trajectory of injury. So we feel that time is like a single track that can only go forward. But in front of the lowest physical rules of the universe, this sense of direction has not been engraved into any fundamental law. In other words, it is not so special now, and the future is not really unreachable. Even in the past, it may not be as far as we thought. But if all this is true, then a bigger problem will emerge. If time can be curved and injury gives it direction, then can we travel through it against the arrow of time? To answer this question in more depth, we need to tell a real little story. Do you remember the astronaut who did not exist in his own country in space? He is Sergei Krikalev. To be honest, he is the most legendary space traveler of that era. In nearly 20 years, Krikalev carried out 6 space missions in total, staying in space for a total of 803 days, 9 hours, and 39 minutes. In other words, he spent more than 2 years on a track a few hundred kilometers away. In the space station, he watched the sunrise and sunset pass by at an amazing speed. The rhythm of that time was so fast that people on the ground couldn't even imagine it. His astronaut career can be said to be across an era. Starting from the Cold War in 1988, he first boarded the Soviet Union's TM-7 spacecraft and arrived at the Mir space station, which is a symbol of the glory of the Soviet space industry. Later, He returned to Mir many times, living in a low-gravity environment, working for a few months, with limited supplies and harsh conditions. But he never complained. He also made his name for being calm, hard-working, and able to stay away from home for a long time. But in 1991, he was still on a space mission, and the Soviet Union on Earth suddenly disintegrated. He suddenly became a citizen of a country that no longer existed. However, as the Cold War ended, space exploration moved from the enemy to cooperation, and Krikalev also became a witness to history. He began to work with NASA astronauts to build a spacecraft and participate in the cooperation of the International Space Station, and became one of the core tasks. In 2000, he participated in the first long-term astronautic mission. 5 years later, he stepped into space for the 6th time, and this time his space accumulation time officially broke through 800 days and set a historical record at that time. In these missions, Krikalev experienced the space daily life of a very small number of human talents, floating around to eat, floating around to sleep, in a wet environment, and even on the track. He is not a tourist who comes back in a few days, but a real human representative. But more importantly, he is not just a space traveler. From a certain perspective, he is still a real time traveler, because he has really been to the future. You didn't hear it wrong, that's it. Why do we say that Krikalev is a time traveler? Because when he flies on the orbit of the space station, the speed is fast, 7.66 kilometers per second, which is about 27,600 kilometers per hour. This is not a dart, this is flying around the Earth. According to Einstein's The Theory of Relativity, a principle is very clear. The faster you move, the slower time will pass for you. This is called time expansion. So when Krikalev flies on the orbit, his body and the clock around him are actually a little bit slower than the time on the Earth. For example, a second after the Earth, he may have just passed 0.9 seconds, which is extremely small, but it does exist. You may think this small difference is not worth mentioning, but don't forget he stayed in space for 803 days in total. Add up all these differences, which is about 20 milliseconds. In other words, he is 20 milliseconds younger. Does it sound like a joke? But this is not science fiction, this is a physical phenomenon. The small difference means that he did jump in time. When he came back from space to the Earth, his present is slightly ahead of us. He lives a little bit more than those people who haven't left the Earth. To put it bluntly, it's not that he went into the future faster, but that we passed the time. This is not a myth. In 1971, American physicists Haffel and Keating did an amazing experiment. They took 4 precise atoms and put them on commercial planes to fly around the Earth. Then, they compared the speed with the speed of light. The result was really different. The theory of Einstein is exactly the same as Einstein's theory. Time dilation does exist. This effect has a special equation called the time dilation formula from the theory of relativity. You don't have to look at the formula, just remember a core point. The faster you fly, the slower the time is for you. In everyday life, we don't notice it because our speed is slower than the speed of light, like an ant climbing. But it's different in space. The speed of a spaceship is fast enough to fly more than 28,000 kilometers in 1 hour. Even if it's only a few milliseconds slower, it can be measured. And if you can fly close to the speed of light, then the time dilation is not just a millisecond, but a terabyte. Imagine you board a spaceship flying at 99.9% speed for a year, and then return to the Earth. As a result, you find that the Earth has been gone for decades. The people around you may be old and even gone. and you only feel that after a year, your present is no longer on the same line. You can imagine this process as someone else watching a movie at normal speed, and you are watching it at slow motion. As time goes by, you and their plot progress will be more and more disconnected. The movie has already been broadcasted to them, and you have just seen half of it. This is the feeling brought by getting close to the speed of light. Your time is slow, and the universe's time is fast. But don't think that only speed can change time, and gravity can also play a big trick. In the theory of relativity, Einstein told us that gravity is not a kind of pull. It is actually a high-quality object that makes the space-time structure around it bend. This kind of bending not only affects the direction of space, but also affects time itself. The closer you are to a mass, such as a star or a planet, the slower your time will be. This is called gravitational time dilation. It is also the least intuitive part of Einstein's theory of sin and karma. In the movie Interstellar, there is a scene that makes countless audiences stare in amazement. The astronauts flying the ship fly like a super big black hole called Gargantua. They landed on a planet that is close to a black hole, and it was this choice that made them almost say goodbye to their own era. Because the gravity of the black hole was too strong, it distorted the space-time around it, not a little bit, but exaggeratedly. The time on this planet is 70,000 times slower. Staying there for an hour, it has been 7 years. They did the task for just a few hours, and returned to the orbit to find that the teammate who stayed on the ship was over 20 years old. This picture looks like a sci-fi movie, but you should know that this is not a random story. This setting was designed by Nobel Prize-winning physicist J.P. Soren in person. He is a scientific consultant and uses Einstein's general relativity to ensure that the black hole settings and the time difference are all real physical phenomena. And this is not a special effect that can only appear next to the black hole. Even in everyday life, the gravitational time dilation can really be measured. In the 1970s, scientists did an experiment. They took two super high-precision atoms, one on the seabed and the other on a 2,300-meter high mountain. As a result, 11 days later, the clock on the top of the mountain really moved a little faster than the clock on the seabed. Why? Because the top of the mountain is farther from the center of the Earth, and the gravitational force is smaller. The space-time is not so curved, and the time is a little faster. And the clock on the seabed is closer to the area where the Earth's mass is larger, and the time is a little slower. How small is the difference? Only a few hundred millionths of a second. But at that time, the instrument was sufficiently precise to be clearly measured. So you see, whether it flies fast or relies on gravity, it can change the speed of time flow. But if we want to talk about the real future travel, we have to look at the third way, the most scientific and the craziest one, that is, to distort the space itself. In 1994, the physicist Miguel Alcubierre proposed an idea that shocked everyone. He said, instead of making the spaceship fly faster and faster in the universe, it is better to make the space itself move. His idea is like this. If you can use the mathematics of general relativity to make space-time into a special structure, you can make a bubble. In this bubble, time is normal to you, but the bubble is moving at a super speed relative to the outer universe. Simply put, the spaceship itself does not need to fly at a super speed, but you sit in the bubble and let the space move with you. As a result, the outsider sees that you fly over a few thousand light years, and you only feel that you have been on a short journey, like driving from the city to the outskirts. It sounds like a crazy story, but in mathematics, it can really be calculated. Usually, when we talk about travel, we imagine a car running on the highway from the starting point to the end, relying on speed, fuel, and a whole route. But in Einstein's general relativity, space and time are not a backdrop. They are like a huge elastic cloth that can shrink, bend, and wrinkle. If you can control the shape of this cloth, then you don't have to run in space at all. You just need to put a hole in it. Alcubierre's idea is so bold. He proposed to wrap a special space-time bubble. This bubble compresses the space in front and stretches the space behind. And the spaceship stays in the middle of the bubble and doesn't move. But the bubble is moving. It's like a wave sliding on the surface of the universe. That's why the spaceship can reach faster than light without moving and doesn't violate any physical law. You can imagine a space-level surf. Alcubierre's drive is like holding this space-time cloth and pinching it into the shape you want and sitting in the middle so that the whole universe doesn't roll you around. The point is not just running fast, but it can also make you jump to the future. Why? Because in this bubble, the flow of time is completely different from the outside world. You may only spend a few months or a few years in it, but it's been hundreds of thousands of years. Imagine leaving the Earth in 2100 and flying to a distant planet. You think you've only been flying for a year. But when you look back, the Earth's calendar has been flipped to 3,100 years. You've jumped for a whole 1,000 years, but you're only 1 year older. And what's more amazing is that in the bubble you can't even feel the acceleration, because you're not moving, but you're being carried by the whole space. So there's no sense of regression. There's no tension in your bones. There's no need for a strong shield to block the dust. It's like sitting on a lake floating without moving, and the whole universe is passing by you at the speed of a madman. But here's the problem. How do you make this bubble? In fact, you need a very special material called negative energy, or strange matter. This kind of matter is not an attractive thing, but it rejects everything and can make space expand and deform. It sounds like magic. In fact, in quantum mechanics, it does have a bit of a twist. For example, the Casimir effect can detect a bit of negative energy between two metal plates. But there's a problem. The amount is incredibly tiny, far too small to do anything significant. To bend space itself, you'd need a staggering amount of negative energy, far beyond anything we can currently create. In the early model, it may be equivalent to the mass of an entire planet like Jupiter. Of course, you can't make it, but there's still hope. An experimenter. Eagleworks once studied this problem seriously. The researcher Harvard Sony White recalculated and proposed an improved model. He said, if you optimize the geometric shape of space, it might only take the energy equivalent of a single car. This is not yet achievable, but it's much more reliable than Jupiter. At least now, we can still discuss this problem, not just close the window. Of course, the problem is still big and scary. If you really want to make that bubble, you have to do space surgery, or the level we can't do at the moment. And even if you make the bubble, new problems will appear. How to make sure it doesn't collapse. How to prevent it from spitting out deadly radiation. Each of these challenges carries its own risk. Theoretically, that twisted bubble may keep accumulating a bunch of quantum radiation. If the bubble collapses at some point, the released energy can not only destroy the spaceship, but also the surrounding space area may be destroyed. But even if there are these super troubles, Alcubierre's drive is still exciting, because it does not break any physical law. It is completely in line with the framework of the relativistic theory. It's just that our technology is far from it. But if you really jump into the future, there is another crazy point to talk about. It's called white hole. We all know the black hole, right? It swallows everything in its path, stars, planets, even light itself. Nothing can escape its gravity. But have you ever heard of the white hole? It's the exact opposite. It is the sprayer. It does not absorb matter, but sprays matter and energy outwards. You can understand it this way. The black hole is a monster that swallows you in one mouth. The white hole is another monster that spits out with one mouth. It sounds like a brain hole. But in fact, this idea directly comes from Einstein's relativistic theory. When scientists solved Einstein's equation, they were surprised to find that in addition to the black hole, there may also be a mathematical inverse. The black hole is something that you can never get out, and the white hole is something you can't get in at all because it keeps spraying outwards. What does this have to do with time travel? The key is that some scientists guess that the black hole and the white hole may be connected through some kind of space-time tunnel, which is the wormhole we are familiar with. If you really have a way to live through a black hole, then you may be spit out from the white hole on the other side, and the extreme gravity will allow you to travel through space-time, not cross-space, but cross-time. For example, you dug into the black hole through the wormhole and dug out from the white hole. It may have been 4,025 years. For you, this journey may be a few hours, but it has been 1,000 years on Earth. You are still alive, but the Earth has changed a generation of civilization. From this perspective, the white hole is like a one-way time accelerator. It won't take you back, but it will throw you to the future. The problem is that the white hole is still just a fake object on paper. We have seen the black hole, and even took its photos. For example, the ultra-high quality black hole used the entire telescope array to get that classic orange donut image. But what about the white hole? At present, there is no direct observational evidence. Some scientists guess that maybe in the early days of the universe, or under some extreme conditions, the white hole appeared briefly. Some people also think that this is a monster that came out of the mathematical equation, and nature has never produced such a thing. There are also some bolder guesses that those extremely mysterious gamma radiation in the universe may be the white hole spitting energy. But in the end, this is just a guess without any evidence. But this idea is enough to attract people, isn't it? If the white hole really exists, if we can get close to it without tearing it into pieces, maybe we can really use it to shoot ourselves into the distant future. It's like finding a secret channel left by the universe to the brave, a shortcut that can cross time. But if these methods are too selective, you still have a choice that sounds down to earth. Move yourself and wait for the future to come to you. This is not science fiction or high-tech magic. Its core principle is a word: wait. Pause yourself and wait for decades, hundreds of years, until the future becomes worthy for you to wake up. This is the so-called low-temperature freezing technology. It's not time travel, it's time to pause. The operation process sounds like the beginning of a science fiction. When a person announces death, note that it is death in legal terms. The freezing company immediately intervenes and uses liquid nitrogen to quickly cool the body to -196 degrees. The goal is to minimize the protection of brain cells and organ structures to prevent rot or irreversible damage. Then put you in a metal jar and put you in a special liquid nitrogen warehouse and keep moving like this until the future has the ability to wake you up. You may not know that this thing has already been done. In 1967, a psychologist named James Bedford became the first frozen person in history. He is still lying in the freezer today, quietly waiting for the miracle of future technology. After his death, many people followed him. Some choose to point their heads to bet that the future can rebuild the body. Some simply freeze their whole body as if the whole person was in the warehouse. It sounds ridiculous, but compared with drilling into white holes and twisting space, this method is the most practical and most operable future travel method. But this method has a lot of problems. The biggest problem is that we don't know how to thaw the frozen person safely. Because when you freeze a person to nearly 200 degrees below zero, tiny ice crystals, and these ice crystals will tear off the cells like a knife and destroy the tissue structure. Even if you use the so-called glass solution to prevent freezing, the chemical toxicity may also cause the cells to suffer. In other words, even if you freeze perfectly and want to recover, it is still a big problem. So freezing yourself is essentially like buying a super long ticket and betting on the future of mankind. It really has the ability to solve the technical problem that looks like a science fiction today. But if this ticket is hit, low temperature freezing is a real one-way time travel. It's not because the time around you is getting faster, but because you stopped and let the world speed up. Suppose you are frozen today and you wake up in 2,500 years. For you, nothing happened, just closed your eyes. But when you open your eyes, the present is another era. This idea sounds really exciting. It doesn't need to twist time and space, and it doesn't need to build an impossible superfast engine. The charm of low-temperature freezing is that it is a very human time travel method. It's not as cool as the Alcubierre bubble, and it's not as unreachable as the white hole, but it's more daring. It's not a certain theory, right? It's science, technology, and a bit of human luck that can fulfill this future dream. In these future leap methods we talk about, low-temperature freezing is the only attempt that someone is really doing now. The probability of its success may not be high, but it is an experiment full of hope. A game about whether the future can be saved in the past, a pause button with life in it. It's hard enough, but if you're not satisfied and just jump forward, do you want to go back the other way around? Does it sound completely impossible? But if you dare to study physics, those seemingly unreasonable weird circles, you'll find that it's really possible. There's a movie you've probably seen. It's one of the most classic time travel moments in movie history, one of which is in Back to the Future. Marty McFly gets on the modified sports car and drives it for 88 miles per hour. That's not a random number. 88 miles is the starting point of the magnetic fusion machine. And then a dazzling white light sprays fire from under the wheel, and then Marty is thrown out of 1985 and into 1955. The entire world has lost the familiar neon lights and has become a retro black and white TV, an old man's car, and a passerby wearing a wool coat. This is an era that you know doesn't belong to you at all. This setting is so charming. You don't need a time machine or high-end theory. You just need to drive and step on the accelerator to travel through time. It's like changing a highway, not to another city, but to another era. But we all know it's not that romantic, but don't laugh in a hurry. Physicists have really studied whether time can be guided like space. It's not walking to the end, but turning around and going the other way. Speaking of Back to the Future, we've talked about a bunch of time-traveling movies that can be paused and frozen at the speed of gravitational expansion and gravity. But Back to the Future is the ultimate challenge. Ironically, the same theory that explains black holes, general relativity, also suggests a few ways out that aren't completely impossible. One of the most intriguing possibilities is the wormhole. You can picture it as a tunnel that suddenly opens up in space, not a door, but something far more mysterious. It's more like an underground dark river entrance and exit that can cross 10,000 light years and even cross 2 moments. Back to the Future takes time travel like a teenager's adventure game. You step on a dot, run away, change the time, and fall in love. But from start to finish, it doesn't explain a word. How time is twisted. That's the difference with Interstellar. Nolan's setting is not just cool, it's as close to science as possible. The second half of the plot is directly face-to-face with a high concept. Time is not a straight line, it can be distorted by the gravity of the black hole. Do you remember that water planet? Cooper and the others stay there for a few hours and then return to the orbit. They have been there for more than 20 years. They spend a few hours on the spaceship for decades. But what really shatters the three views is the latter one. Cooper voluntarily fell into the black hole. According to all physical common sense, he should have been crushed into a basic particle. But he didn't die. What he fell into is not the dark, but the super space. A highly constructed, a space that should not exist. In there, time is not linear, not the past, now, and the future. But all moments are spread out like a giant web. Every moment is visible. Every second can be touched. He saw every time point in his daughter's childhood room spread out like a poker card. And he is not the one who holds the card, but the one who sits between the poker cards. He didn't walk in time, he wandered in time. What's more terrible is that this is not a coincidence. The setting given by the movie is that the future high-dimensional intelligent body, that is, the human himself, will create the superspace and send it back. Then, he will fall into the black hole. So, this loop isn't a mistake or a paradox. The first action sets the ending in motion, and the ending itself triggers the beginning. It forms a self-contained loop in time and space, a closed cycle where the past and future continuously create each other. At that moment, Cooper was not saved by the black hole, but he was saving time. This is the coolest part. Cooper did not fall into the black hole, nor did he enter the high-dimensional space, but he did not change the past, nor did he make a paradox. Everything Cooper did in the hyperspace has already happened. He did not change history. He just became part of that part of history. From beginning to end, he was the one who sent the gravity signal. It was only until he entered the hyperspace that he finally realized that person had always been himself. He did not rewrite the timeline, but he completed that timeline. The future and the past are entangled here, but they have no impact on each other. There is no split timeline. There is no parallel universe. Everything is self-contained. It may sound like a paradox, but it isn't. In physics, there's a special concept known as the closed time-like curve, or CTC. The next part will give a brief explanation of what it means. Time is not a straight line, but a curve that can be closed. You walked around inside, the starting point and the ending point are actually the same moment. Everything happened, and it can only happen that way. There is no more, and there is no less. Time is not being rewritten here, but being completed. This is the most shocking meaning of Cooper in the hyperspace. He didn't actually travel back to the past, but he was able to influence it. It's as if he reached through time and touched it, without ever truly stepping into it. This is a form of time travel that doesn't break the timeline. It is not a time travel, but a time travel from a higher dimension. But the question is, if you really send the whole person back, is it really possible? Surprisingly, it is possible in physics. How to achieve it? In theory, it is a passage that opens two remote time points. You don't have to climb slowly on the surface, but you can go through the tunnel under the cloth and jump to a very far place like a super nebula, or even another time point. Imagine that the universe is a huge piece of paper. You have to walk from the top left corner to the bottom right corner, according to the regular route for a long time. But if you fold the paper in half, stick the two corners together, and then poke a hole, you can go through it directly. This is the point of impulse. Physicists have a formal term, Einstein's Rosen bridge. It's like a bridge that connects different time points, and it's not just space. Time can also be connected. If the right parameters are aligned, the portal could take you not only across great distances, but also back to the distant past. It's no longer just about where you go, but when you go, and even beyond that. If time flows differently at each end of the portal, it stops being merely a shortcut through space and becomes a true time machine. What's happening here? Do you remember the concept of time dilation? Imagine you attach one end of the time portal to a spaceship and let it travel close to the speed of light, while the other end remains on Earth. The passage of time at each end will begin to differ. The end aboard the spaceship, moving at near light speed, will experience time much more slowly, while time on Earth flows normally. When the two ends of the portal are reconnected, their clocks will be completely out of sync. So, from the end of the Earth, you may come out of the end of the flying and jump directly into the past. If you go the other way, it's to the future. Which way you go determines whether you are ahead or behind. You can think of it as a ladder, going down while flying fast and coming up slowly on the other side. Which side you choose determines whether you go back to yesterday or tomorrow. In theory, if you go in the right direction of the impulse, you can really go back to yesterday's Earth. But soon you will find that the time travel of the impulse has a cruel limit. You can only go back to the moment when the impulse was created. You can't go earlier. For example, if the time portal was created in 2100, you wouldn't be able to return to 2050 or even to the age of dinosaurs because the path didn't exist before that moment. This is also why, in science fiction, travelers usually go toward the future. Time is a one-way passage. Going back to the past is where it really becomes mind-bending, the most fascinating yet forbidden realm. In theory, the time portal could take you back to your own past, allowing you to see your younger self. It sounds wonderful, almost unreal. But of course, there are challenges, and each one is greater than the last. To begin with, the portal would need to be stabilized by some form of exotic matter, since ordinary matter couldn't possibly withstand the immense gravitational forces at its entrance. Only strange substances with negative energy density can pull in the opposite direction, blocking the channel. The problem is that we have never really found this kind of thing. In theory, there is a quantum effect, such as the Casimir effect, which can measure a little negative energy, but it is too little, too unstable, not enough to build an impulse frame. Second, the portal is extremely fragile. Even a small burst of radiation, a stream of particles, or a slight tidal fluctuation in space could cause it to collapse instantly. Imagine being halfway through only for the portal to suddenly shut its door. You are not unable to get out, but you are torn into pieces by the whole spacetime. Third, the most strange paradox. If you can really go back to the past, is it possible that you can do something to completely change your own history? For example, you stop your grandfather so that he never has a chance to meet your grandmother. Then, will you still exist? For example, you receive a message in the future telling you not to go on a certain trip. As a result, you really listened, did not go, and avoided a disaster. So where does this message come from? This is the so-called grandfather paradox and information paradox. It sounds like time travel will mess up the entire logical system. But surprisingly, from a purely physical point of view, the general relativity does not prohibit these things from happening. It even allows a phenomenon called the time curve. You go around a circle, and when you come back, it just happens to be the moment you left. All events are interlocked, there are no contradictions, and they are self-completed. It sounds unreasonable, but it's about math. This concept was studied by physicist Kip Thorne, a leading expert in theoretical physics. His conclusion is both simple and astonishing. If a stable wormhole could be created, it could, in theory, serve as a time machine, without violating any laws of physics. Did you hear it clearly? It's not impossible, it's just that we are far from being able to do it. So next time someone says time travel is impossible, you can laugh. Because it's true, it's still impossible now. But don't forget, the universe under our feet is too big, too strange, and too insolent. It's never in line with our common sense. It's full of paradoxes, full of loopholes, and full of opportunities. History has always taught us one thing. If humanity is given enough time, the impossible eventually becomes reality. Perhaps one day, we won't just imagine a time machine, we'll create one.